Hello everyone, this is Dr. Webb. In this video we're going to talk about curvature. So curvature is probably, a term that's not foreign to you. It's used in everyday life. But this is, we're doing math. And so if we're doing this in math, this must have we need some precise mathematical definition for this. So what exactly do we mean when we say curvature? So we start off with R of t as a smooth parameterization of a curve. So remember, smooth parameterization, what this is saying is that its derivative is non-zero, never is not the zero vector. Essentially that it has speed, has positive speed at all times. Then what the curvature of a curve is, we'll call it kappa. That's a little Greek letter kappa. The curvature is going to be the magnitude of the derivative of the unit tangent vector divided by the speed, the magnitude of velocity. Okay, so how should we think about these two things? So t is your direction. T prime then is change in direction. Right, and so you can think about this top value here is talking about change in direction, while the bottom, so r prime, the magnitude of r time, we think about speed, so it's kind of talking about per distance. Right, so curvature is talking about how much you're changing in direction per the distance traveled. So putting that together, so when we put those two together, the curvature is telling us exactly how much the curve is turning at that given point. So what if kappa is big? Well, if kappa is big, that means a lot of change of direction. Over not much distance. And so a lot of change of direction in a short amount of distance, that's turning very sharply. What if kappa is equal to 0? Well, if kappa is equal to 0, the only thing that could be equal to 0 here has to be t prime. And so this means no change in direction. And if you're not changing your direction at all, that means you're going in a straight line. And so when kappa is equal to 0, the curve is linear at that point, right? And so kappa small means closer to linear, less change in direction. Okay, so here's an example, similar to the same example we used in the last video, except now we're trying to find the curvature of this curve. So this is drawing out a circle of radius 4. That almost looks like a circle. So to get the curvature, we need to get the unit tangent vector. And so we need to get r prime first. So derivative of 4 cosine is going to be minus 4 sine. Derivative of 4 sine is going to be 4 cosine. And then we can see that the speed, magnitude of this is going to be, we can pull the 4 out, and then it's going to be sine squared plus cosine squared, which is 1. And so speed here is always going to be 4. And so then that means that the unit tangent vector is minus sine cosine. And so its derivative is going to be minus cosine minus sine. well, what's the magnitude of this? I think we saw this on the last video before. Well, the components are both a sine and a cosine, so you square them and add them together. You get 1. And so to get our curvature kappa, it's going to be t prime, magnitude of t prime, divided by magnitude of r prime. And that's going to be 1/4. So the curvature, and so this happens for all values of t, for this circle is 1/4. And so this makes sense that the curvature of a circle would be a constant. If you're traveling along a circle at a constant speed, and so it is traveling at a constant speed 4, then you're always turning the same amount. So what if instead we're trying to find the curvature of a line? Well, as we saw before, the curvature of this line should be 0, but let's double check this. So this 1 plus 3t, 2 minus 4t, 5 plus t, all the components are linear, so overall r of t is describing some line. And when we take the derivative, first component 1 plus 3t is going to give me 3, minus 4, 1 is my velocity vector. It's constant for all t. What's its magnitude going to be? Well, that's going to be square root of 9 plus 16 plus 1, which is square root of 26, although I didn't really need to calculate this because once I have r prime, well, t is 3 over square root of 26 minus 4 over square root of 26, 1 over square root of 26. But you can see this is a constant vector. So when I take the derivative of a constant vector, I'm getting 0. So magnitude of t prime is 0, and so then this means that kappa has to equal 0 everywhere. So traveling along a line, curvature is always equal to 0. You're not curving at all. Okay, so geometrically, what exactly is this curvature telling us? Well, if we take the reciprocal of it, that reciprocal is going to give us the radius of a tangent circle to the curve, of the tangent circle to the curve. So similar to how we can draw tangent lines to the curve, we can also draw a circle that matches the curve most precisely at that point. Call it a tangent circle, or really the technical term is it's called an oscillating circle. And so then the curvature is then the reciprocal of the radius, right? So a smaller radius, if we have a small radius for the curve, that means a lot of turn. If we have a big radius, so let's say that's the curve at that point, big radius means not so much of a curve. So small radius, sharp turn. Large radius, more gentle turn. Okay, so let's give sort of a quick, well, we'll see how quick it is, geometric argument for how this works. Okay, so remember that our kappa is equal to magnitude of t prime divided by the magnitude of r prime. Okay, so let's use some basic facts about derivatives from Calc 1. So t prime, this is going to be roughly, if I pick a spot and move over by delta t, t prime is roughly going to be that, the difference between t prime at t plus delta t minus t, and then dividing by t prime. R prime, similarly, is going to be difference between r at those 2 points over delta t. And so this is just basically, this is coming from the limit definition for derivative, that if delta t is small enough, what the limit means is that these values are going to be very close to those differences. So let's make a picture of this. So let's say we have some curve, okay, and so let's say that this is where we are at t, and then if we move over delta t further, that's where we are on the curve. Okay, and so then that's going to be my unit tangent vector at t, and that's going to be my unit tangent vector at t plus delta t. Okay, and so these two, so remember these are tangent vectors, so they're on the unit circle, and so looking at this, t of t looks like it's, that should just be t of t, not t prime. So the unit tangent vector at t is roughly there. Unit tangent vector at t plus delta t is roughly there. And so this difference between them right there, that's going to be roughly t prime at t times delta t. And I'm just solving for that in that equation. Okay. And so, and this also is giving me a little triangle right here. Okay, in fact, it's an isosceles triangle because these two sides are both length 1. And then t prime of t is giving me the length of this side right there. Okay, now these are both tangential to the curve at those 2 points. If I drew along the normal vector at each of those points, so normal vector is perpendicular. Normal vector is perpendicular. Well, those two are going to cross each other at this point. And this is a fact from geometry that this is actually giving me a radius of a circle between 2 points. Right? And so this is going to be my radius r. Okay. Let's not confuse it with r. Let's make it look, well, let's just call it r. Okay. And then what's the vector between these 2 points? Well, that's the change in the curve. That's the difference between these 2 points right there. Right? So that side right there is going to be roughly r prime of t times delta t, because that length is that length right there. And so if I solve for that in this equation right here, that's what I get. R prime of t times delta t. Okay. Now, this last bit, so now I have this second triangle where these two radii are going to match up, and then this length here is r prime of t. So this is about length r. This is about length r. R prime of t times delta t. Okay. Now, the last trick from geometry I'm going to use is that these two angles are this. When I say these two angles, I mean this angle here is going to be equal to that angle there. And this comes from the fact that we're going to have so we're going to have two congruent triangles, but they're going to be different. They're going to be different sizes. So these are two not congruent, but they're two similar triangles of different sizes. So it's a little bit of geometry to see that these two angles are the same, but it has to do with the fact that we have two perpendicular angles here. And so the shift in both of them is going to result in the same shift here to the shift there. Okay. If you don't believe me, you can go back to your high school geometry book and double check that works. But it is true. So we have two similar triangles. The length of one triangle is r prime times delta t. Really, it should be the length of that. The length of the other side is the length of t prime times delta t, right? And so, since these are similar triangles, the ratio of t prime delta t over, in magnitude, over the magnitude of r prime t delta t needs to match the ratio of the sides of these isosceles triangles. And so the size of this, the length of this side of this isosceles triangle, well, it's going along a unit tangent vector, so its length is 1. And then the length of this one is coming from the radius of this circle. And so that's radius there. And so, as you can see, my delta t's here cancel off, and so I have the magnitude of t prime over the magnitude of r prime, and that is the curvature. So the curvature is 1 over the radius. Okay, so there are a number of other ways to get curvature rather than using the magnitude of t prime over the magnitude of r prime. So the first way is if you happen to have in hand the arc length parameterization, or your curve is already in the arc length parameterization, well then r prime of t is always 1, or r prime of s is always 1. That's what it means to be the arc length parameterization. So then the curvature is just the magnitude of t prime in terms of s. Okay, and so again, this is coming entirely from the fact that in the arc length parameterization, the speed function is a constant 1. Okay. So here's another formula. The derivation of this is a little bit nasty. There's not any geometric intuition that comes in really. And so I'm going to kind of leave out the derivation of this. It is just a little bit of algebra. Well, more than a little bit of algebra. It's just a lot of algebra. And there's no, even though we have a cross product in here, there's no there's no real geometric interpretation about why that cross product comes in. It's just sort of a artifact of the algebra, that the algebra makes sense here. But the one thing I will say about this formula is that often, given some perhaps nasty, or even not even all that nasty, this formula might be an awful lot quicker to compute than the magnitude of t prime over the magnitude of r prime. In particular because you don't actually have to figure out what the unit tangent vector is. It's all wrapped up inside of r prime of t cross r double prime of t. And so really the secret behind this one is really what you need to show is that the magnitude of the derivative of t prime is equal to the magnitude of r prime t cross second derivative over the speed squared. And so if once you convince yourself that this is true, and this is just a lot of algebra, then magnitude of, this formula for kappa follows immediately from that. Okay, so let's leave it there, but let's allow ourselves to use it. Okay, so for this example, we're going to calculate the curvature of an xy plane of t squared t. And so if you look at this, what curve is this drawing out? It's drawing out y squared equals x, so this is a parabola on its side. And we want to do it specifically at the point 4, 2. And so if we're at the point 4, 2, what's the t value for this? Well, looking at the y coordinates, the t value is going to be 2. Okay? And so we're looking at calculating the curvature at 2. And so we're going to use this formula, r prime at 2 cross r double prime at 2 all over the speed at 2 cubed. Okay, so we need to get r prime. So r prime is going to be 2t comma 1. And so if I plug in 2, I'm going to get 4 comma 1. And then its magnitude at 2 is going to be square root of 17, I believe. Right? 16 plus 1 is 17. Take the square root. And then r double prime is going to be just 2, 0. Okay, and so then to take a cross product, remember we just add 0 in the other component. And so r prime at 2 cross r double prime at 2 is this determinant I, j, k, where my components r prime is 4, 1, 0. R double prime is 2, 0, 0. And then let's copy these out. There's only one diagonal that's going to be non-zero. And so that's going to be this diagonal. All the other ones have a 0 in them in some way. And so the value of this cross product is going to be, since this is a diagonal going up, it's going to be negative, so it's minus 2k. And so the magnitude of this is 2. And so then kappa is equal to, is going to be 2 divided by speed cubed. And so this is going to be 17 to the 3/2. Okay. And so one thing I should note, which I don't think I said earlier, even though we're doing all these calculations with t, as you change the parameterization, the curvature is not going to change at all. And so, in fact, you can think about the t prime of t, that actually, the speed, the change in speed comes in there quite a bit in calculating that. And so the curvature is something inherent to the curve. Even though we're doing all these calculations using parameterizations, if you change parameterizations, that change is all going to cancel out along the way. Okay, one last little bit about motion along a curve, and which really is kind of hard to find a place to stick this in, but this is a good place because curvature is going to come into play here. And this is what's called the tangential and normal components of acceleration. And the idea here is that if anywhere on a curve, moving in, particularly in 3 space, in 2 space it's not surprising, but in 3 space it's maybe a little bit surprising. But if we're moving along a curve, we pick some point, we can draw the unit tangent and the unit normal at that point. The acceleration vector is going to be lying on the same plane as the unit normal and the unit tangent vector. Okay, this is a fact that it has to happen. And if you think about this, the unit tangent really comes from taking the first derivative, r prime, and then the unit normal comes from taking the second derivative, which is involves is going to involve r double prime in there, and so that's where the acceleration is going to come into play. Okay. And so what we can do then is that means that we can write the acceleration vector as a linear combination of the unit tangent and the unit normal vectors, right? So we can write it as a sum with them with coefficients. The coefficient of the unit tangent vector is the tangential component of acceleration, and the coefficient of the unit normal vector is called the normal component of acceleration. So what does this tangential component and normal component tell us? Well, let's sort of figure out what we're getting. So remember that the acceleration vector is the second derivative of our vector function, right? And the second derivative is just the derivative of the first derivative, right? So it's d over dt r prime of t. Well, we want to get the tangent and the normal involved in some way, and the tangent's involved to r prime of t. And so we know that if I take r prime of t and divide by the speed, this is giving me the unit tangent vector. And so we've got r prime of t here, r prime of t here. And so if I want to solve for r prime of t in this, I'm just going to multiply the speed over. And so the derivative of r prime of t really is equal to the derivative of speed times the unit tangent vector. Okay, and this is where we're going to start doing our derivative at. And it might be a little bit easier if I'm going to think about this speed here. I'm going to give it another name. I'm just going to call it v of t. So it's not a vector function, it's just v. V for speed, velocity of t, times the unit tangent vector. And so then they're getting multiplied together, so it's a product. So we need to use the product rule. And so the product rule says, well, I'm going to get my speed, derivative of speed, times the unit tangent vector, plus speed times t prime of t. Okay, well, t prime of t, we want to get the normal vector involved in here in some way, right? And so recall that the normal vector is equal to t prime of t over the magnitude of t prime of t, right? And so then we get that t prime of t is equal to its magnitude times the normal vector. Okay. Well, we've also seen the magnitude of t prime of t come in with curvature so far. And so remember that curvature is equal to t prime of t divided by speed. And so here we're using v of t to be speed. And so t prime of t by itself, the magnitude of t prime of t by itself is going to be curvature times speed. Okay. So then putting this all together, I've got t prime of t here is equal to the magnitude of t prime of t times the normal vector. But then the magnitude of t prime of t is curvature times velocity. So putting this together at the end, I have derivative of speed times the unit tangent vector plus I've got v times kappa of v, and so this is going to be kappa v squared times the unit normal. And so here you see we've written our acceleration as, well, we've got, this is a scalar times the unit tangent plus, this gives me another scalar times the unit normal. Okay, so let's clean up and write this nicely. So a of t was the derivative of speed. So it's the derivative of the magnitude of r prime of t, right? And so a of t is telling us about change of speed. So this is talking about change in speed. And then the normal component is curvature times velocity squared, or speed squared, right? And so if the tangential component is talking about change in speed, so it's talking about acceleration or deceleration, what's the normal component talking to you about? So remember, kappa is talking about the radius of a circle. It's the reciprocal of a radius of the circle times the speed. And so really what this is talking about is the centripetal acceleration. So a of t is talking about your linear acceleration or deacceleration. The normal component, a sub n, is talking about the acceleration that's causing you to turn, right? So a of t is talking about linear change in speed. And then centripetal acceleration, this is talking about acceleration to turn. Acceleration to turn. Okay. And so if you're thinking about, something moving, especially if it's changing speed, if you're turning your car and on the gas, some of that gas is being used to make you increase your speed forward, and some of that is actually being used to turn you. And you can feel that force pulling you, pulling you in towards the turn. Okay, so let's end this video with an example. So we're given here an object is moving in space, and we're given the velocity vector 1, 3, 2, and the acceleration vector minus 4, 3, 1, and we want to find the rate that the speed of the object is changing. Okay, well, so one fact, so we know that the acceleration vector is going to be a sub t times the unit tangent plus a sub n times the unit normal. So we figured out in the last one what a sub t and a sub n mean. How can we quickly get them? Well, because the unit tangent and the unit normal vectors, since they are both unit vectors and they're orthogonal together, that means that I can get a sub t by dotting, taking the dot product of a and t, and I can get a sub n by taking the dot product of a and n. And so this is coming from the fact that t and n are perpendicular to each other and their magnitudes equal 1. And so anything that I can write as a linear combination of those two, that means I can get those coefficients by just taking the dot product with the two individual vectors. So this is just a fact from linear algebra, but it's nice to know in this. So how can we use it here? Well, our velocity vector is 1, 3, 2. So what's our unit tangent vector? Well, it's going to be the velocity vector divided by its magnitude. And so this is 1, 3, 2, and its magnitude is 1 plus 9 plus 4, right? So 1 plus 9 plus 4 is square root of 14. So this is 1 over square root of 14, 3 over square root of 14, 2 over the square root of 14. Okay. A sub t then is going to be what we get when you do minus 4, 3, 1, and dot it with the unit tangent. Square root of 14, 3 over square root of 14, 2 over square root of 14. And so what's this going to be? So this is going to be minus 4 over the square root of 14 plus 3 times 3 is 9 over the square root of 14 plus 2 times 1 is 1 over square root of 14. And so then putting this all together, minus 4 plus 9 plus 1, so that's 11 minus 4 gives me 7 over square root of 14. And so that is telling us what our change in speed is. And so because this is positive, this is saying that the speed is increasing. At this rate. If we had gotten a negative value for this dot product, then that would have mean that the object was decelerating, but the speed is increasing, so it is accelerating at this point at the curve. So that is all for this video. I will see you again soon.